Okay, everyone, welcome back to ELEC3204. Today we're going to do a revision session for the optical part. So basically, the exam questions are going to be from lecture 4 to lecture 7. Your coursework is based on lecture 1 to lecture 3. So at this stage, what I'm going to do today is to go through the past exam papers that you have access to. So Liliang, he sent you exam paper from last year, and then on the course website you can download exam papers from 2014 to 2019. So please ignore the exam paper for 2014 to 2015 because the course was designed differently back then. So after 2015, the optical part of this course hasn't changed a lot. So it's really important to go through exam papers. You don't have the exam answers. I'm not going to give you answers today, but we're going to look at those exam questions together and go through the knowledge that is related to these questions. And some of them are very, actually all of them are quite basic. So past students, they always respond that always feedback that the optical part is easier than the other two parts because you only have to remember 3 sets of equations from lecture 4 and lecture 5, which are the responsivity and the capacitance and the SNR. That's it. So 3 sets of equations, and then some more concepts from lecture 6 and 7, including MZM and modulation schemes. So all the exam question answers actually they are based on the slides. You don't need to answer anything further from the slides, from what is defined by the slides. It's really important that you practice you practice on a piece of paper before the exams, because many of the examples you see on the slides, they seem very simple, but at the exam you probably would feel nervous and then you make mistakes. So it's really important to practice to walk through all the exam questions if you have time to, and also practice before the exam. Okay, so first of all, let's look at the exam paper from last year, which Lilian has sent to you. So first question, a typical point to point intensity modulation and direct detection system is shown here. So basically we want you to derive different modulation schemes that can modulate these binary bits. So these binary bits are at location A, and then you need to use different modulation coding schemes and draw the waveform or optical phase of DPSK at B, which is electrical input to MZM, C, which is optical output from MZM, and then D, which is electrical output from photodiode, photodetector. Okay, so let's look at dual binary first, because NRZ is the most simple one. We'll just look at it at the end. So let's look at dual binary first. So for dual binary encoder, we change the mapping from binary data to encoded beta a little bit. The reason is that we want a narrower optical bandwidth. We'll look at that a little bit later again. So sometimes we do coding either for favorable bandwidth performance or better error performance against noise or dispersion. Okay, so suppose we have binary input, and then we have the we have A, and then we have B. So if we initialize A as 0, then first B is obtained by XOR between the binary input and A. So first we have from 0, 0, we get 0 for the first B. And then this B is delayed to be the next A. So B is delayed to be the next A. So the next A is also 0. And then the next input is 1. And then A is 0. Then the next B is 1. So the next A is 1 here. And the next A is 1 here. Okay, and then you work out the following. You work out all the rest. And then basically the B is obtained by binary data, and A, they perform XOR. So the first row, second row, XOR, you get B. And then the output, the encoded data, is obtained by B, aids A. So if you have 0, 0, then the output is 0. 1, 0, output is 1. And then 1, 1, output is 2. So be careful here. The binary input will have 0, 1, 0, 1. So binary bits. And then the encoded data, after encoding, we'll have 0, 1, or 2. Okay, and then you work out the rest. So, so this is a dual binary encoder, and then we input this into MZM. So MZM converts electrical input to optical output. So because we have 3 levels, 0, 1, and 2, we use two-way pi. So we use the whole transfer function that converts electrical data to output to optical output data. So when the input is 0, optical output would be on. When electrical input is 1, the optical output will be off. When the electrical input is 2, the optical output will be on. So on, off, on. So if we look at the waveforms, this is from the from slides. It's not exam answers. So you have binary data in, and then you get encoded data based on the previous slides. You have input binary data as 0 or 1, and then encoded data as 0, 1, or 2. And then you map them to the MZM's input. So this is B, point B in the exam question. So 0 is mapped to -pi, 1 is mapped to 0, and then 2 is mapped to pi. And then based on the transfer function, based on this transfer function, -pi is on, 0 is off, pi is on. So we have the optical signal is on for -pi, off for 0, and then on for pi. So this is C, and then point D here is output, electrical output of the photo detector. So we have on decoded as 1, off decoded as 0. So basically we come back to binary bits, binary data. So be careful here for dual binary. In the end, here we have to reverse all the electrical data. So if we reverse this 1 to 0, 0 to 1, then this is exactly as the first line, the data input. However, the exam question asks asks just the output of the photo detector. So point D here should be the waveform of this one. So I labeled D here, should be this one. Point C is the optical input to the photo detector. And then point B is the encoded data waveform. Okay, so this is what is expected for the answer. So basically, if we look at the question again, we give you a string of binary data. First, you need to work out the encoded data binary. Sorry, 1 or 2 or 0 or 1 or 2, and then input it to MZM, and then optical output would be on and off, and then electrical output will be 1 or 0. Okay, that's still binary. And then DPSK, let's deal binary. And then DPSK, let's look at DPSK. So DPSK, we have these are symbols, and these are input bits. So if input bit is 1, then symbol is unchanged. If input symbol is input binary bit is 0, then the symbol is changed from 1 to 0 or 0 to 1. So here we start from a symbol being 1, okay? And the binary bit, first binary bit is 0. So if we have 0, we need to change it. So the next symbol will be 0. We change it. And then so this is the same as this one. So 0 would change the symbol. So encoded symbol would be 0. Okay, and this is also the next symbol because we change it. And then if I have input is 1, then we do not change the symbol. So the output is 0. This becomes reference of the next one. It's also 0. And then input binary bit is 0. Then symbol need to change from 0 to 1. Okay, and then this is a reference for the next one. And then input binary bit is 0. We need to change the symbol from 1 to 0. And this becomes the reference for the next one. So you can continue work out the rest. So based on this encoded data, the transmitted phase is when we have 0, we modulate the optical phase as pi. When we have 1, we modulate the optical phase as 0. So because it's BPSK, we only have optical phase of either 0 or pi. Okay, so if I look at DPSK receiver, because we modulate symbol onto the phase change between every 2 consecutive signals. So as a receiver, we can just interfere the received signal with its own delayed signal. Okay, so as a receiver, when there is an optical phase change, we know the binary bit should be 0. When there is an optical phase change, we know the binary bit should be 0. And optical phase change, we have 0. All the rest are 1. So we decode the binary bit, which are the same as the binary bit as the transmitter here. Okay, so if we look at the question again, we want a waveform at point B, point C, point D. So B is input to MZM, C is optical. So here we want optical phase for DPSK in the question. here, optical phase for the DPSK. And then we have D is the electrical output. So basically for DPSK, we are expecting the waveform B like this. And then waveform for C is here. And the waveform for D is here. Okay, so these are optical phases for C. So all the values, all the binary bits, they are a bit different from year to year. So it will be, and they are very different from the binary input. So the binary input here in the slides, it would be a good idea if you practice on the exam questions before exam. The binary bit input would be different for the exam compared to the example. And one last coding scheme we haven't said is NRZ. So NRZ here. So NRZ is very simple. We only have high for 1, low for 0, high for 1, high for 1, and 0 for low for 0. So the electrical input would be just high for 1 and then low for 0. And then the optical input will just be on for 1 and then off for 0. And then as a receiver after photodetector, what you get would be the same. So high for 1, low for 0. Okay, so NRZ is very simple. Okay, next question. Draw the circuit diagram of DPSK optical receiver and explain its operation principle. So basically for DPSK, we modulate the binary bits onto the phase change between every 2 consecutive symbols. So as a receiver, we can just interfere the received signal with its own delayed version. We do not need a separate laser. We do not need a polarization control because this is interference between itself. And then if the 2 signals they constructively interfere, it means if we didn't change the phase between the 2 consecutive symbols, then it's binary 1. If they destructively interfere, it means we did change the optical phase between every 2 consecutive symbols, then it's logical 0. Okay, so we output the interfered signal into photodetector. So normally we have photodetector and then amplifier, and then make decision based on the intensity. So that's an explanation. So basically, your answer does not need to go beyond any further from the slides. So if we look at the explanation on the slides, what we expected, first of all, we have the phase difference between 2 successive symbols. So basically it's BPSK, so one symbol only have 1 bit. So we interfere, so we use MZM with 1 bit delay here. And then, so on one arm, we have a delay that's set to be a simple period. So we interfere the signal with its own delayed version. And when the 2 consecutive bits, they are in phase, it means we didn't change the optical phase. So it's logical 1. If they are out of phase, then it's logical 0. So we can decide this based on the intensity here. Okay. Okay. So next question. A diagram of MZM with traveling wave configuration is shown here. So assume EO bandwidth of MZM is 20 gigahertz, but we modulate return to zero scheme with 40 gigabits per second data rate. So how do we do that? So first of all, okay, we look at this page again. So basically, for return to zero here, the symbol period is reduced by half. In this way, we created more pulses, more edges of pulses, so the receiver can detect the start of phase better. So it's better for synchronization. Otherwise, if you transmit a lot of zeros for non-return to zero, the receiver wouldn't know for sure if a lot of a period of off is switching its transmitter completely being switched off, or the transmitter is transmitting zero. So by creating more pulses, the receiver can do synchronization better. But the disadvantage is that we reduce the symbol period by half. This means in frequency domain, we double the spectrum. So basically, for let's come back here. Basically, if we want 40 gigabits per second data rate, then for non-return to zero, we only need 20 gigahertz bandwidth. But we only need 20 gigahertz bandwidth. But for return to zero, we need 40 gigahertz bandwidth. So that's the background. Another question asks you, how do we still drive this circuit by 20 gigahertz bandwidth for return to zero? So first of all, so this is again some explanations, and then in the end, your answer doesn't need to exceed the scope of the slides. So this is from the slides, but but this is also some of the background. So essentially, to modulate return to zero, we need a clock signal, and we need data signal. So this data signal is exactly the same as non-return to zero, and then we multiply this with a clock signal. So if we want 40 gigahertz, 40 gigabits per second data rate, then the pulse period, what is a period? It's peak to peak. So this is 25 picoseconds. This corresponds to 40 gigahertz. 40 gigahertz. So in order to obtain this optical bandwidth, we need to drive the electrical signal with 40 gigahertz for the clock signal. And then for the data signal, it's the same. We drive it with 40. So we know that for MZM, the transfer function is actually cosine function. But sometimes we shift it by pi. So it becomes like this. It's all because of the device. Sometimes we shift by pi. Sometimes we use left-hand side of the transfer function. Sometimes we use right-hand side of the transfer function, because even the ideal cosine function is not linear. It's not a linear mapping between electrical signal and optical signal. And then the fabrication of the device is further away from ideal. So when we get the device, we sometimes shift the transfer function by pi. Sometimes we use left-hand side, sometimes we use right-hand side. This is just a bit of background. In the exam, if you can use left-hand side or right-hand side for either one of these. They are all okay. Okay, so for the clock signal, we need 40 gigahertz to drive the electrical signal and then get 40 gigahertz optical bandwidth. So how do we get, how can we only use 20 gigahertz drive signal? We use the whole region of the transfer function. So that as the first half of the input signal, we get output of this. And then if we only use the left-hand side, then the second half, what we get would be something like this. However, now we use the whole region of the transfer function, two-way pi. So the first half, for the first half, the optical output is peak. And then for the second half, the transfer function is inverse of the first half. So what we have is another peak. So this reduces peak to peak by half. When we reduce peak to peak by half, we double the spectrum. That's why we only need half of the bandwidth to drive a higher bandwidth optical signal. Okay, so the key here is to use two-way pi, and we use the whole transfer function. So that's clock. So once again, for MZM, it could be cosine function, it could be it's shifted. And the previous slides, this is shifted by pi. So in the exam, whichever you choose to use is okay. So the summary on this clock MZM is that when we drive the electrical signal with two-way pi, then we have doubled frequency, doubled spectrum. So we use 20 gigahertz to drive electrical signal, and then we get 40 gigahertz optical bandwidth. So the difference between the two transfer function is that they are shifted by pi. So they are equivalent. So in summary, for return to zero, we need to have a clock signal, and we need to have a data. So we have two MZM. So for first MZM, we can only use 20 gigahertz to drive a 40 gigahertz. So output is like this. So we have 40 gigahertz optical bandwidth. And then for data, we still use only half of the transfer function. We do not always use two-way pi. It consumes too much power. Also, the transfer function is not ideal. So we do not always get the pulse that we desire. But this is a special case. Whenever we use two-way pi, we can save half bandwidth. So this is equivalent to before. The transfer function is shifted by pi. Okay, so summary on the previous figures. So I highlighted the key points that I expected from your answer. So first of all, the drawback of RZ is that we reduce the pulse duration to half. So this doubled the required bandwidth. So if we want this much data rate, for NRZ, we only need half of the bandwidth. But for RZ, we need 40 gigahertz bandwidth. So in order to generate RZ signal, we need two MZM. So these are the keywords. You don't need to remember word by word, but the keywords are very important, and it would help me to mark you if you kind of break down your explanation and highlight your keyword. So you need two MZM, and to generate the clock signal with 20 gigahertz drives electrical signal, you need to use two-way pi. You need to use the whole region of transfer function. And then you have the second modulator MZM, the same as before. It is for the NRZ signal. So you kind of concatenate two MZM. Two MZ. So this is a summary for the question. Okay, next question. For the optical receiver, we have quantum efficiency here, and then wavelength here, and then you need to calculate the responsivity. And if you want this much of current, then you need to calculate how much optical power is required. So this question is the same as all these questions from past papers from other years. Okay, so responsivity is a measure to evaluate the efficiency of the optical detector. So the definition of responsivity is the output current divided by the input optical power. So we have the photodetector, we have the optical power input photodetector, we have the optical power input, and then we have the current output. And then quantum efficiency is related to the material. So it's defined as the number of electrons collected divided by the number of photons collected. So we have number of electrons collected and the number of photons collected. So the relationship between this one and this one is that we have this number of photons, and then we know one quantum of energy is hf. H is Planck's constant, f is frequency. So h is normally given to you. And then the relationship between these two is the current equals to the number of electrons multiply charge on one electron. This is also a constant that will be given to you in the exam paper. So in summary, we have the output current in this equation. So quantum efficiency is here, and then this is optical input power. This is charge of one electron, a constant that will be given to you. Quantum efficiency was given to you in the exam question, and then h is Planck's constant, and it will also be given to you on the exam paper. F is operating frequency. So basically, you have speed of light divided by the wavelength. So wavelength is given to you. So responsivity equals to so you have the wavelength here that's given to you, and quantum efficiency, charge of one electron, speed of light, Planck's constant. If we look at an example from slides again, so this is not exam answer, but it is the same as in the same format as the exam question. So basically, we change the value, the values here every year. So you have quantum efficiency, you have the wavelength, you put wavelength, quantum efficiency, and then this is charge of one electron, and then Planck's constant is h, speed of light is c, so you can calculate r, responsivity like this. And then next you have the target current of this level. You need responsivity to help you to calculate how much optical power is required. So basically you have a responsivity and then the current in the question. So responsivity, you calculate it from the previous step, and then you get the optical power. So be careful about each step, because if you calculate this wrong, later on in the later sub questions, you need to use responsivity to calculate other things. they will be wrong as well. So be careful about every step. So next question, if we assume the total capacitance for the front end is CD, then calculate the resistance that allows this pulse detection bandwidth. So basically, the optical detector together with amplifier is equivalent to RC circuit. So if you look at here, so this is from slides, it's equivalent to RC circuit. So for any RC circuit, bandwidth equals to 1 over 2 pi resistance and then capacitance. So if you know the bandwidth and if you know the capacitance, you can calculate the resistance. So this is an example from the slides. For the exam question, we have different values, but in the same format. Next question, calculate the root mean square noise. When we have this load resistance calculated from the previous step, and then we have the temperature here. So basically, for the optical detector, we have the thermal noise. We have two sources, two types of noise. One is thermal noise that's only related to temperature. Be careful here, this is absolute temperature. So the temperature that's given to you on the exam question, is temperature in degree. So you need to convert it to absolute temperature, T here. And then load resistance you calculate from the previous step. Bandwidth you calculate from the previous step. And then K is a constant. Another source of noise is shock noise. So basically, shock noise has two parts. One is called dark current, and not noise. Another part is quantum noise. They are opposite to each other. So for the photo detector, ideally we want to receive light and then produce current. So dark current noise happens when there's no light yet, but you already have current. So it's dark, no light yet, but you already have current. So that causes noise. Quantum noise is the opposite. It happens when we have light already, but there is no current. So quantum noise, we have light already, but there is no current. So we have two sources of noise for the shock noise. So this is a current produced by the photo detector, and this is a dark current. We'll calculate this a little bit later. This specific question only asks thermal noise, right? Only asks for thermal noise. So we only need to use this equation. So if we look at example from slides again, so we have load resistance, we have the temperature, and then bandwidth is also from the previous step. And then we have temperature here, and then we have load resistance. K is a constant that will be given to you, so you can calculate the thermal noise. Next question. So assume here, dark current is given to you here. So you need to calculate SNR. This also tells you the noise figure of the electrical amplifier. So if you go through the slides again, so this is from slides. First of all, we have two types of noise, thermal noise and then shock noise. And then shock noise has two parts, the dark current that's given to you, and this is quantum noise. So the whole noise power is related to the total current multiplied. So the whole noise power is related to the total current multiplied the total bandwidth, and then E is the charge of an electron. So another part is for the thermal noise, you need to multiply this with a noise figure. So noise figure is given to you in the question. So you have the thermal noise multiply the noise figure, and then you have the shot noise, and then the signal power is a square of the current produced by the photodetector, which you either calculated from the previous steps or is given to you by the exam question. So if you look at an example from slides again, which is in the same form as the exam question, first of all, we calculate the thermal noise. So we did that already. And then we calculate the shot noise, which have the dark current noise and then quantum noise. So we calculate all of this as the shot noise. We know the noise figure is 3 dB. We multiply this to the thermal noise. So we have the noise figure multiplied by thermal noise, and then we have the shot noise. Wait, let me check. Yeah, this is shot noise. And then signal power is current power produced by the photodetector. We calculated this from the previous steps. So eventually SNR is in this form. Okay. So next question. The above optical receiver is deployed within a 40 kilometer optical fiber. And then you have transmit average power of this much. And then the distance, this is a distance of fiber, you have the loss. And then you have the extinction ratio more than 10 dB. And then you have the wavelength. Now you need to calculate SNR. So I can't give you directly give you the answer, the value for the answer. But we can go through the steps together. The first step, we know the transmit optical power is this much. And then the total loss in fiber, we have 50 kilometers, and then it's 0.2 dB per kilometer for the loss. So first step, we can get the received average optical power, which is the transmit optical power minus the total loss in fiber. Okay, now we get the receive optical power. Second, as I mentioned in class, in lecture 5, I think, when extinction ratio is very high, it means that the optical power for logical 0 is just 0. The optical power logical 1 is 2 times of the average. So I have power for logical 1, power for logical 0, and then we have the average. So if this power is 0, this power is twice of the average. So we get the optical power for logical 1. And then we need to use responsivity to convert this optical power to the output current. And then we use this output current to update the SNR of the previous steps. So you see we have the current here. And then for the shot noise, we also need so basically we need that current to update here and also here. All the rest of the correlations are the same as before. Okay, then finally you get the SNR. So if you practice by yourself, do it step by step, and in the exam, even if your exact value of your final answer is not correct, I will still give you a proportionate mark for different steps. Okay, let's look at more exam questions from previous years. So this is a diagram of MZM with a traveling wave configuration. So it explains its basic operation principle. So as I explained in lecture 6, there are 3 levels of MZM operation principle, 3 levels. The expectation on the first level is that we have 2 arms, and then we have optical signals travel on 2 arms. We want to change the speed of the two optical signals so that when they combine together, they can interfere either constructively or destructively. This gives us the degree of freedom to modulate the optical signal. So how do we change the speed of travel of the optical signal? We apply an electrical field. So basically, we can apply forward bias and reverse bias. Remember, when we apply forward bias, we expel the free electrons by the negative contact. And when we apply reverse bias, we try to hold the free electrons away from the other contact. So this would change the electrical field of the optical signal. So this change the travel speed of the optical signal. So that's an extra explanation. If we come back to the slides, for the first level of the MZM, first of all, what we want is to change the refractive index of the 2 arms. So that the optical signal in one arm would be faster and the other arm would be slower. And then the signal would combine again as the output. And the 2 signals from 2 arms, they would interfere. So this interference would cause large variation in intensity. That's how we modulate the optical signal. So we modulate the optical signal by electrical signal. So this is the first level of MZM principle. The drawback of this is that when we apply the electrical signal into the metal strip here, the electrical signal would travel this way and this way. What we really want is that the electrical signal would travel towards the same direction as the optical signal, so that they interact for a longer period of time. So this gives us the second level, which is a transmission line. We use transmission line. So this is a traveling wave configuration. Okay, so the metal strip, they are arranged as transmission line, and then electrical input is from here, and then at the other side we have impedance matched, which means we have termination, so that electrical signal would just go this way without coming back as reflection. So this resistance should be the same as the characteristic impedance of the transmission line. For simplicity, you can just call it termination, and you can just say it's impedance matched to the transmission line, so that the signal wouldn't reflect back. This means we want the electrical signal to travel towards the same direction as the optical signal. So this means the electrical signal travel in parallel with the optical signal. So this would create a long interaction period. So the advantages of this traveling wave configuration is summarized in here. So first of all, we make the device more efficient, and then we allow lower voltage because we effectively enlarge the period of time for electrical field without increasing the voltage. We just increase the time of interaction between the electrical signal and the optical signal. We also simplify the wiring because originally we wire the the metal strips, kind of the wiring would cross the arm. But now we apply electrical signal input from two separate metal strips from two separate metal strips, so the wiring becomes simpler. And also this makes possible higher modulation rates because it's more efficient. If we apply separate plates, we can modulate different amplitude level, for example, palm 4. We'll look at that again a little bit later. So let's come back to the question. Right, how MZM works. So this is the second level. We have traveling wave configuration. The third level is that the transfer function is a cosine function between the electrical signal and optical signal. So the cosine function is not strictly linear. This means the input amplitudes, they are equal spaced, but the output optical signal will have a bigger gap in the middle than the gap at the sides. So what we normally need to do is we need to adjust the bias and also adjust the amplitude so that we only use a small section, small region that is more linear, that is considered linear. So the third level is we apply heater on both arms so that we create bias. So basically, we fabricate with heater, and then with heater, and then apply extra DC voltage onto heater. So how do we change the amplitude? We change the length of the metal strip. We'll look at this again a little bit, just in the next few questions. We'll have similar questions to this later. But basically, the length of the transmission line, it is proportionate to the amplitude, because basically this is a decreasing or increasing function. The longer the input interaction, the higher the output amplitude. Okay, so 3 levels of explanation for the MZM. Next question, explain the advantage of dual binary coding scheme over conventional coding scheme when we use WDM, so wavelength division multiplexing. Okay, so background knowledge. You don't need to draw this in the in exam. So basically, we have the WDM receiver like this. So eventually, we want to separate different wavelengths. So what is desired is that we want the spectrum, optical spectrum, or the line width to be as narrow as possible. So here, they are separated. So a little bit more background knowledge, how this works is that we have a mixture of all wavelengths. Then they have a free space propagation at 2. And then for 3, we have different lengths of waveguides. But in each waveguide, the signals, different wavelengths are still mixed. And then from here to different output ports, everything happens before this point. What we want is that for different wavelengths, they go to one output port constructively interfered from different waveguides. Okay, so I have one wavelength that is constructively interfered at one output port. So the output would be like a rainbow because for each output port, we only have one wavelength. So we want the optical spectrum to be as narrow as possible. So do you remember for dual binary code, the input is binary 0, 1, and then output we have 0, 1, or 2. So in this way, we can use two-way pi. So we map 0, 1, and 2 to binary optical output, so on or off, and then on. Sorry. So eventually we convert the binary data to data that contain 0, 1, or 2, and then eventually we convert it back to binary data. We go through all this trouble because rule of thumb, whenever we use two-way pi, we narrow optical bandwidth. So dual binary occupy narrow bandwidth. That is beneficial for the WDM, because for WDM receiver, we want different wavelengths to be separated. So for different wavelengths, we want bandwidth to be as narrow as possible, so they can be separated. Okay, next question. So explain how MZM works for POM N. So here we want you to draw a diagram for POM 16. So basically, one way to do it is first of all, we have one transfer function, and then we input different amplitude for the electrical signal, and then we output different amplitude for the optical signal. There are two drawbacks for this model. So here we have only one transmission line, right? So there are two drawbacks of using this model. One is that, first of all, we need digital to analog converter. We need to convert the binary bits into electrical signal, and then we need to map electrical signal to optical signal. Another drawback is that this line is not linear. So for multiple amplitude, we need to adjust bias and also the amplitude. So in order to avoid this, what we want to avoid is we want to avoid digital to analog converter for multiple amplitude. So how do we do that? We use multiple transmission line. So for example, if it's POM 4, then we have two logical bits. They control, so we have 4 amplitude levels. One bit is in charge of the smaller amplitude level. Another bit is in charge of the higher amplitude level. So we use a shorter transmission line for the first bit, and then longer transmission line for the second bit. In this way, we avoid digital to analog converter for using a single transmission line for multiple amplitude. Okay. So if it's a POM 4, we'll have two logical bits. So I have two segments. Then we need so I have two segments. Then we need independent timing control. So we apply delay here that map the delay of the optical propagation delay, the propagation delay of the optical signal. So I have the two delay. The amplitude of these two, they are not exactly, so it is not exactly that the first one is half of the second one, because the transfer function is not linear. We adjust the length here to be proportionate to the first one, in accordance to the input-output relationship of the transfer function. So basically here it only says the transmission line is not exactly twice the length needs to be adjusted. So this is Palm 4. The question asks you to draw a program for Palm 16. So it's similar to Palm 4. You only need to change the wording here. So whenever it says 4 amplitude, for Palm 16, you have 16 amplitude. And then for Palm 16, you have 4 logical bits, right? And then in the end, so this is Palm 16. Okay, next question. So you have this optical detector. They ask you to decide the drift time and the capacitance. So basically, we have this PN junction. So for optical receiver, we do reverse bias. So we hold the electrons in N-type as strong as possible to be away from the other side, so that in the middle region, the depletion region, ideally there's no free electrons, there's no free hole. So when we expose this region to optical light, we can absorb a quantum of energy and then create a new electron and a hole pair. And then the electron will move to the negative contact, hole will move to the positive, the hole will move to the negative contact. The electron will move to the positive contact. So there's a trade-off here. The width here, we want it to be larger so that we can expose a larger area to the optical light. We can collect more photons. However, the larger the width is, the longer the time for drifting for the free electron to travel to the positive contact. So first of all, we need to calculate drift time, which is proportionate to the width. So the carrier drift velocity is a constant that will be given to you on the exam paper. So if the width is given to you as well, you can calculate the drift time. And then the bandwidth is like this. So 3 dB bandwidth for the photo diode rule of thumb is like this. So you do need to remember these two equations, but you do not need to remember that value for the drift velocity. This is a constant that will be given to you. So one example from the, okay, one more thing is capacitance. So normally the width and the area, they are given to you in the exam question, and this is a constant that will be given to you on the exam paper. So one example from the slides, that's in the same form as the exam question. You have the drift time. You need to calculate drift time based on this. And then you need to calculate the capacitance. You just put all the values in. You have the cross area. There is one here. And this constant is epsilon here. And then you have the width, which is this one here. So you put all the values in. You can calculate drift time, bandwidth, and then capacitance. This is one set of equations that's related to capacitance. Okay, one last question. So engineer decide to increase the width, right? So it can reduce the drift time. So the engineer wants a higher bandwidth. Is this possible? So if we look at the equation relationship between equations again, we can see that when we here, when we reduce the width, we increase the drift time. And then when we increase the drift time, when we reduce the width, we reduce the drift time. When we reduce the drift time, we can increase the bandwidth. But be careful, this bandwidth is the bandwidth of the photodiode. When we talk about the bandwidth of the whole post-detection bandwidth, we need to also consider the capacitance here. So capacitance of the photodiode is this. So we reduce width, then we increase the capacitance. And for the whole circuit, we have a photodiode, and then we have a amplifier. So the whole circuit is RC circuit. We have resistance, we have capacitance. The whole bandwidth equals to 2 pi RC1. So you need to match the load. So you have the required bandwidth here, 10 gigahertz required bandwidth. The capacitance need to contain the capacitance of the photodiode and the capacitance of the amplifier. And then the load resistance need to match the value of these two. So in the exam, if you worry that some parameters are not given to you, just give a discussion on these trade-offs. So first of all, when you decrease the width, you decrease the drift time, and then you increase the bandwidth for the photodiode. But the whole bandwidth of the circuit determined by the total capacitance. So we know that reduce the width, we increase the capacitance of the photodiode. And then the total capacitance would be increased here. So you need to match load resistance with this capacitance in order to get a target bandwidth. So that's all the exam questions that you have access to. So once again, I emphasize all the lectures lectures 4 to 7. Okay, lectures 1 to 3 are only related to coursework. And also please ignore exam paper in the year of 2014 to 2015 because the course has changed its scope after 2015. So that's all for the revision. Next time I will do revision for the wireless part.